Okay, so from last time, so remember on Tuesday, we're thinking about two ways to represent the change in accumulation, starting from x equals 1 and then to make it a function, terminating or ending at any value x. Okay? So hopefully we all got open form. We all got the open form. Y equals what? What would the function be in open form? That would be the accumulation function, starting accumulating at 1 with this rate of change function. In open form, what's the key structure of this? What's the structure of this function? I heard one person say it. What's the overall structure of this function if it's open form accumulation? Integral. Integral. Starting at 1. Until x are something besides x. So use t. There's the open form. There's the open form. So you could also have, instead of r of t, you could have 1 over 1 plus t squared. All right, so that's what we've already defined r as that. So we can do it that way, or I could have done 1 divided by 1 plus t squared. Same exact thing, because that is the definition of the rate. So you can put the actual rule for the function in, or you can use function notation, either way. Okay, so now closed form, what's the general structure of that going to be? The general structure of this closed form function, though. Final minus initial. Final value of accumulation minus initial value of accumulation. Which means that we need a function whose rate of change is 1 over 1 plus x squared. Is that, yeah? Yeah, and that's what she said as well. So the function whose rate of change is 1 over 1 plus x squared, we recognize from the mastery test as arctan. So we could also write y equals, so on graphing calculator, it's a tan or a sine or a cosine. It means arctan. A tan of what? Final, so it's the final value of the accumulation minus the initial value. So x, then, minus arctan of 1. So I've got blue and purple here. When I graph both of these, I should just see one black graph, okay? Blue plus purple equals black, all right? One black graph, so that because they are the same. Or indigo, it is, thank you. One indigo graph. One indigo graph. Purple plus blue. There it is. Why do we know that it's starting accumulating at 1? What?
Y equals 0.
Y equals 0 at x equals 1. So there we go. At x equals 1, accumulation is 0. And then as x increases, we have accumulation. Okay, so that's really distracted to those around you. So please, I can't make you pay attention, but I can make you be quiet. So you gotta give the people around you the chance to be able to concentrate. All right, so starting at x equals 1, the accumulation is 0, and picking up from there. But so we keep saying it's starting at 1, but then what's going on over here? So we never really addressed. Yeah, the accumulation is 1 at x equals 0, or at x equals 1. And that's all good. But it's kind of like, did it really start accumulating here? We've got accumulation graph back here, right? So this is still all part of this accumulation function. So did it really start accumulating at x equals 1? Where did it start accumulating? Yeah, so I could zoom out here, then I could just move over. Here I am at negative 200. I could zoom out some more. Here's negative 1500. Okay, so it's like he said, it's kind of like, reset graph. It's kind of like it had already started accumulating way, way out at negative infinity. But then when it got to 1, we were thinking of it starting accumulating at 1, and that gave us that 0 at 1. So we kind of need to change the way we're thinking about this, because if it were truly starting accumulating at 1, the graph would look like this. That's truly starting accumulating at 1. But there's more out to the left. So it's kind of like it had already started accumulating. And when we got to 1, it was 0. So how can we think about this? So let's think about this. Remember our sand loading example. Okay, so remember our sand. If we have a rate of change function r, the accumulation function r is defined by integral from a to x rt dt, right? Where f of x is some antiderivative of r, okay? F is r is the derivative of f, so f is the antiderivative of r. So remember our dumping sand onto the scale. So we have the accumulation function is from a to x rt dt. Suppose, say right here, you know that scales, if you put some weight on a scale, there's a reset button. If you leave that weight on the scale and hit reset, it reads 0. And then if you put more weight on the scale, it will only read the additional weight, although there was already weight on there. Are you familiar with that? Okay, really, really important. So it's kind of like we start loading sand onto the scale, and then at x equals c, we're going to hit reset. So at time c, what will the scale read? 0. So at time c, the scale will read 0, although there's a bunch of sand that's already accumulated onto the scale. Okay? So the total accumulation, so in our example here, a is 0. That's where we truly start accumulating. So we're going to start accumulating at a, which is, in this case, time equals 0. The total weight of sand at x seconds is going to have 2 parts. It's going to be the first amount of weight that we put on before the reset, and then the amount of weight accumulated after the reset. So it's going to be the integral from a to c plus the integral from c to x. That should make sense. So this is the total weight from time equals 0 up till we reset. That's that weight that's sitting there. Then we reset, so the scale doesn't read this anymore. And then the scale starts reading more weight that we put on after the reset. So then this is truly the total weight of the sand, even though the scale isn't reading it all. Make sense? So we got the weight accumulated in the first c seconds up to the scale reset, and then the weight accumulated after the reset, the scale reading. And the sum of those two is the true total weight of sand on the scale. So what we're going to do is we're going to just solve this algebraically for this one right here. So what is the scale reading in terms of the other? So the scale reading is going to be the total weight of the sand minus the weight that we put on in the first c seconds, right? So it's just going to be the total weight of sand on the scale minus how much we put on before the reset will be the amount that the scale reads. Well, the total weight of total weight on the scale is just f of x. And then the amount up to the reset is just f of c. Okay? So this is the scale reading after the reset. or the accumulated amount after the reset? It's simply the total weight of sand on the scale minus the weight before the reset. Okay, so this gives us a new way to think about these open form integrals. Rather than thinking about the accumulation starting there, we can think about the accumulation resetting there. That the accumulation already began before, and we're just forcing by this lower limit of integration, making it c. The accumulation has already started, but we're going to force at some x value, we're going to force the accumulation to start over and reset and be 0 there. And then we're going to track the accumulation after that. Okay, so it's the same thing we had before, right? It's the antiderivative at the final minus the antiderivative at the original, but now we have kind of a different meaning for this. Rather than the accumulation starting there, it's like the accumulation resets there. Okay? So this is a more kind of a more coherent way to think about it, because we've got graph way out to the left. There's more graph before where that accumulation was 0 at this x value. So this kind of takes care of that. This idea takes care of that. Does it make sense?
It's kind of like a stopwatch in a way.
Okay.
Although that's like one measuring only one quantity.
Okay.
You let the time go, and then you press like the lap button, and it starts.
Okay, like a lap button on a stopwatch. Totally. Yeah, good. Okay, so here's another example. So now we'll frame this the other way now, the new way. Instead of saying we're starting accumulating at x equals negative 2.5, we want to say we want the accumulation function that has a reset at x equals negative 2.5. So that we get zero accumulation at x equals negative 2.5, but we allow for the fact that the accumulation started way out at wherever before that. But we're just forcing it to reset to when it gets to x equals negative 2.5. So we're going to kind of start over. Accumulation is going to be 0, and we're going to go from there. See if you can do it. So here's the new rate function. Open form, closed form, with a reset at negative 2.5. And then write the open form 2 ways, using function notation and using the rule. Just to practice that you can use both. Both are valid, okay? Both are valid. That open form, inside that integral, use the rule, use the function notation. 2 different ways. So we got to really know our mastery rules, right? We're thinking backwards. When we write that closed form, well, we need accumulation function whose rate is this. So can you imagine what accumulation function will have this rate of change function? Only masters of derivatives could think backwards like that. I put both ways that you could do the. Oops. Do you see that both of those are the same thing for the open form? Using the function notation, because we've already defined it in GC, we defined what R was, and then just using the rule. Both are valid. Yeah. Yeah, I forgot the X. Thank you. Thank you. Like that? Now do I have it? Yep, thanks. So what accumulation function will have a rate of change of 4/3 t to the 1/3 cosine t to the 4/3? Matt? Okay, so here's the great thing about this. Take a stab at it. Then what can you do? Take a stab at it. He said, he took a stab. He said, sine of x to the 4/3. Is this what you meant? What can you do now? See if it's right. So yeah, so we could do it and we could graph it, but algebraically, what can we do to see if that's right? Take the derivative, and what should we get? What we started with. That's what's great about this. You don't have to be all frightened that you have to get it right on your first try. Just go for it, right? Go for it, and then take the derivative. If it's exactly what the rate function you were given, then you got it. If it's something different than the rate function, you know you got to adjust, right? And we'll do that later in class, okay? So let's take the derivative. Derivative of this is cosine, or if we want to go inside out, it would be 4/3 x to the 1/3 times cosine of, leave it the inside as it is, right? There's the derivative. Is it what we started with? That's exactly the rate function we started with. So he got it. So the whole thing with this is you can just give it a shot. Go for it, and then you take the derivative of what you think it is, and the derivative should be exactly what the rate function you were given. And it was. So therefore, the closed form function will be what? Somebody knew. How will I set up the closed form? Somebody knew. Anthony.
Y equals sine of x to the 4/3 minus sine of negative 2.5 to the 4/3.
So what? The total change in accumulation is final minus initial, right? Final value of accumulation minus initial value. Make sure you put that negative 2.5 in parentheses. So those are the same accumulation function that have that rate of change function and a reset at negative 2.5. Please.
The green line, isn't that the open form?
No, integral. I just used, no, integral form is open form.
Okay, but
I'm just using the rule instead of function notation.
But do you remember when we talked about if, like the open form of an accumulation function?
Yeah?
The rate of change. You said g of x plus h minus g of x over h. That's the open form. And if you want the closed form of the accumulation, then it's the integral from 0 to x of the rate of
Yeah,
change.
right there. The integral from 0 to x of the rate of change. That's open form. I'm just using the rule instead of function notation. These are equivalent, right? That's what R of t is this. So I'm just substituting in the rule of the function for R of t. Right? This isn't the antiderivative. This is still the rate function.
Exactly.
Yeah, so it's the integral of the rate function. That's open form. Why isn't that open form? Yeah, it's the integral of the rate function. Closed form is the final value of the accumulation function or antiderivative minus initial value of the antiderivative. So again, I'll just turn this one off. Do you see it? Purple plus blue equals indigo. Oh, there we go. Okay, so where does it start accumulating? Negative infinity. Okay, I could just keep scrolling out left, and there's more and more graph to look at. But we forced what to happen? A reset at negative 2.5, so it better be, the accumulation better be 0 at negative 2.5, and indeed it is. If we had a different reset, how would this graph be adjusted? How would you see this graph change if we reset at a different x value? It's going to have the same rate function as this. Shifted up and down. So the graph would be shifted up or down to achieve a reset at a different place and maintain the same rate function for all x values. If you move it left and right, you're changing the rate function. You're getting different values of rate for different values of x. Moving it up and down maintains what? The change in y over the change in x for every x value. So you could think about, tangent lines, slopes of tangent lines, or move it up and down, the rate of change doesn't change, but you get a different reset. Okay? Yes, please.
Right there at the 0 axis for x, 0 for x.
Yeah.
Is it a corner, or is it just a really sharp curve?
Let's take a look. I'm going to zoom in, see what happens.
Sharp curve, guys.
Oh, wait a sec. Okay, so here let's just look at one here. Our approximation is it's using different approximating techniques for each one. So the integral form is breaking down here for small values, so we'll just turn it off. There we go. It's still kind of the jury is out. Is it a corner point?
I don't think so.
Or is the derivative, so if it's a corner point, the rate of change would be undefined. If there's no corner point, then that rate of change would be 0, right? If it has a smooth local minimum. It's looking pretty smooth to me. So how could we verify that? Is the rate of change, wow, that was way too much zooming in. It's not stopping. Help. So, if it's a corner point, then the rate of change would be undefined at 0. If it's a local min, then the rate of change would be what? At x equals 0. If it's a local min, the rate of change would be? Please know this. 0, right? Pause, right? Pause. So, we could visualize it and we could say, well, we're not sure, or we could just look at the rate function and say, if we plug 0 in, do we get 0? Or do we get something undefined? If we plug 0 into our rate function, is it 0 or is it undefined? That will tell us if we have a corner point or a local minimum. Which is it? Does r of 0 exist and equal 0 or not? Can we take 0 to the 1/3 power? Is it okay? Sure, it's 0. Can we take the cosine of 0? Sure, it's 1. So r of 0 is 0 times 1 equals 0, which answers our question. Is it a smooth local minimum or is it a corner point? It's a smooth curved local minimum, right? Because the rate of change is defined at 0. It's 0. Okay, good question. So we've been working all semester To understand the fundamental theorem of calculus, we have arrived. But there's nothing more to do. We've already done it. Let f of x be any antiderivative of f. We think of little f as what kind of function? A rate function. Then the integral from a to x of f of t dt equals what? You can finish it, and that's basically the fundamental theorem. Finish the statement. Everyone finish it by yourself. Everyone in the whole room should be able to write this down, or else you've been somewhere else for the last class and a half. So somebody new. Who's got it? How about right here? Which f? Big F of? Right. That's what it is. This is the fundamental theorem. So it's like, well, duh. We already knew that, right? So it's looking at, we'll talk about it in a sec, okay? So then evaluating that function at a particular value, x equals b, then this is like the second part of it, where you actually calculate a value instead of the whole function. So now we're talking about a value of accumulation, where we stop accumulating at, so we're going to accumulate, we're going to have a reset at a, and then we're going to stop accumulating, truly stop accumulating at b. So we're going to get a number. We're going to get a value of an accumulated amount from a to b. And this is just like plugging b into this function, right? It's just like evaluating this function at x equals b. So that there's nothing new there. But these are the two parts of the fundamental theorem. Okay, so this property has enabled generations of people to do calculus exercises without really understanding calculus. But we've worked all semester to really understand it, okay? So let's review. We want to really understand it. What are we talking about? What is this? This is the accumulation function represented in open form for a quantity with rate function f of t and a reset at x equals a. So we know that's accumulation function when we reset at a up until x, where the rate of change function is little f of t. Okay, and what's the right-hand side? Closed form of the exact same thing. It's just the closed form of the exact same thing. Or typically represented, this is typically closed form. If we can get a closed form for capital F, then this is our closed form representation of that accumulation function with the reset at a. All right, and how do we get those? How do we get the closed form, that capital F function? Well, it's antiderivative, or it's like thinking about all these mastery rules, but in reverse. We ask the question, what function has the given function's rate of change? Yeah, question?
I just want to
Yeah.
the rate of lower percent.
Yeah, when we set up an open form accumulation function, this is the rate function. That's right. This is k delta x, right? K delta x. Just a really small one, a really, really small k delta x, and the integral means what? What does that mean? It looks like the letter S stands for sum. We're summing up a zillion little bits of accumulation. So there, that k, remember that's our rate of change. So now we have the whole rate of change function to the left. Okay, so here's an alternate notation. So we can write this kind of more in a compact way as that antiderivative. So this, what I put in red, means exactly the same thing as what I put a box around. You've got the antiderivative function. You're going to evaluate it. You're going to evaluate it at x equals b. This says you to do a vertical line. You're going to put b in, and you're going to put a in, and you're going to subtract. So these are absolutely equivalent. They mean the same thing. It's just a compact form that you will see. All right, let's do an example. So here's the rate of change of elevation. So we actually worked on this earlier, but now here's the actual rate function. Here's this actual rate function, 52.8 cosine x times e to the sine x plus 2. So let's first graph the change in highways elevation from elevation at the border as a function of the number of miles from the border. Okay? So is this a rate or accumulation that we're going to graph? The change in elevation from the border. Is that accumulation or rate? That's accumulation. Accumulated elevation from the border. So we get that reset at 0. And so starting at the border, we're driving uphill, right? We're driving uphill. We're always gaining elevation. So what is the accumulated change in elevation from mile 2 to mile 5? Represent that on the graph and represent that using the rate function. So again, this is review. So how would we represent the accumulated change in elevation starting at mile 2 to mile 5? How would we represent it on the graph? And how would we represent it using r of x? Go, see if you can do it.
What's the name of the graph?
This is the elevation function. So it's e.
What is it called?
E. So we'll call this e for elevation. This is the function e.
So minus 2.
And how would you represent it on the graph? So graphically, what would that be? Yep, that's right. That's right.
Yeah, on 2 x 2. I have the.
So how about using the graph? How would it be represented using the graph?
Oh, on the
Y values? So you should have thought, oh, I'm going to find e of 5. All right, I'm going to do my best to go straight across here because we want to actually estimate this here.
up,
Up, up, up.
just a little bit up. Okay. It's at
Did I make it to the right place in the end?
Yeah.
All right, here's my estimate for e of 5. 400, what, 95? I'm estimating 495 feet. Is it feet? Feet of elevation, okay? And then you should have thought, okay, I'm going to estimate, or I'm going to look at e of 2. Did I make it to the right place in the end? That's pretty close to 300. Approximately. So we can use just the graph to estimate this quantity that I'm asking, or this value that I'm asking about. What would we estimate the accumulated change in elevation from mile 2 to mile 5 is? About what? $795? 195, right? So it's going to be this right there. That kind of that segment on the y-axis is representing the change in elevation, E5 minus E2, about 195 feet. Okay, now I want to represent, so just a representation using the rate function of this value exactly. So I want to write an expression that would calculate this value exactly. What would that expression be? Somebody new. How can I write an expression using the rate function that will calculate it? Okay, you're new today. Go, yeah.
So e of x. Do you want me to use the second one we used? Because you said.
No, make it short, so use the function notation.
Okay, e of x.
It has nothing to do with e of x.
Well, don't you want the.
I want to use the rate function.
Okay, then the integral
Integral
from 2 to 5
2 to 5
of r of x
r of
dx.
This is what she's offered up. Do you agree with that? Is that exact or estimate? No, that's exact, right? That's the exact amount of accumulation from 2 to 5. Is it okay that we use x's here?
Yeah.
It's fine, as long, so it's because we have a 5 here, right? If we were doing a function, then we just can't have these be the same.
Right.
But if we're actually computing a value of a change in accumulation, then x is perfectly fine, okay? Okay, so what is that? And so this is the same thing as saying e of x would be from 2 to x r of t dt, right? And it's like we're evaluating this function at what input value? So here's our elevation function in open form. We're evaluating that elevation function at what input value if we're doing this? Right here. Is that a hard question? What do you, so how we're now, so the question to find this amount of accumulation from 2 to 5 is a matter of just one output value of this whole function. For what input? X equals what? 5, right? X equals 5. We're saying we're going to do a reset at 2, and then we're going to accumulate to 5. So this is just E of 5. Do you see that? That's what we wrote originally. It's just E of 5 if this is our accumulation function with the input of X, where we're going to stop accumulating. Okay, so let's write that out. Now let's actually put the rule in there. So here that is. 2 to 5, now I'm going to use the rule. 52.8 cosine x e to the sine x plus 2. Well, now we have a way. So now that we're able to get closed form, algebraic, a closed form version of this, algebraically we can find the value exactly. See if you can do it. So can you use now algebra, this new tool we have, get a closed form for that? And a closed form means we can just calculate it easily, right? It's just going to be plugging and chugging. So maybe as a first step, let's make it easy on ourselves. So since it's the whole thing is times 52.8, let's bring that outside. Just get that out of the way. And then we'll have cosine x e to the sine x plus 2. Now we have the ability to solve this by hand. Now we can solve this by hand by getting an open form for that, or a closed form for that open form expression. Right? And the key is fundamental theorem. Fundamental theorem. So you've got two things to work on. The first term and the second term. Are you making progress?
So,
If you're lost, stop me. You should be making progress on this. You want to get a closed form for that thing, or just do it by hand? You want to be able to do it by hand?
this is take the derivative of this.
have to be something. You have to.
Now I'm just doing
It's
this.
just even if it's crap.
Okay, now what about starting at 2 and ending at 5? Starting at 2 and ending at 5. I see lots of people got it. Okay, lots of you got it. So here's this new notation, right? This vertical bar. So what function has cosine x e to the sine x as its rate of change? So you recognize that that is a chain rule, right? That's a chain rule. And you say, oh, e to the sine x, its derivative would be cosine x e to the sine x. And then what function's derivative is 2? What function's derivative is 2? 2x. And then, so now I'm using this new notation. Just write the antiderivative once. You put the vertical bar, and then you put the final x value and the initial x value at the bottom of the bar. And what does that means? The exact same thing as this. Plug in 5, plug in 2, and subtract. Capital F of x minus capital F of c.
I got a dumb question. Does the vertical bar and the closed form have a name?
Maybe. I don't know what it is.
You sound like me taking it.
It's like it's, do you guys know? Is there a name for that? Like evaluate? Just evaluate, right? It represents evaluating that thing at 5, at 2, and subtracting. So, no, I don't know the name. Okay, and so now we can get a number. So now, forget about summing up a zillion bits of accumulation, right? We got accumulation at final minus accumulation initial, which we can just get like that, right? So there's none of this. There's none of this having a computer add up a zillion little bits of change. Integral style, right? Integral style. Instead, it's just, oh, we can get that easily. We can get that easily and subtract. And we should get, we're expecting something about 195. What did it turn out to be? 206. 205.96. So we were 10 feet off. Okay, was that okay? Any questions? Really, these are really important examples, okay? Really important examples. Wait, you want to do another one? Any questions? Last chance, questions on this one? Okay, a culture bacteria in a particular dish has an initial population of 250 cells, and it grows at this rate, 50 e to the 0.3 t cells per day. We want to find the population function, b of t, at any time starting at t equals 0. We want to find the population function at any time starting at t equals 0. So, what can we do? So now we have to, all this stuff that we're learning, can we apply it? Maybe I'll just give you like 2 minutes to see what you can come up with, and then I'll show you my thoughts about it, okay? So, all this stuff that we're learning, can you initiate how to apply it to this? Go, take a couple minutes and see if you can do it. We're trying to write b of t, a population function. Given that the rate function is this, and there's an initial 250 cells at time equals 0. Make one round. Catch me if you got a question.
Oh, B.
No, the rate, it's 250 about accumulation or a rate of change. Yeah, so that wasn't right, but this actually what you got here was right. Well, it depends where the plus 250 is. Is it inside the interval or outside the interval? Outside.
Outside the interval.
Yeah, so you're not going to add it to the rates.
No.
You're going to build the accumulation function, reset at 0. Okay. Start with the integral form.
I think they did the derivative. No, it's not.
No, you want to start at 0. Yeah, but you need that initial period.
I'm going to do 0.3t.
So you want to add t to 0. You want to reset that. Then you want to make it happy with 0. There you want to start. Right. And you need it to be 50 to 0. Outside process. Yeah. So we want a function for any time. So we
Point
0.15 t squared would be 3t.
0.3t.
Oh yeah, 0.3t. Okay, so we want to start or have a reset at 0. We want to reset at 0, and we want it to be a function of where we stop accumulating. So t. So that's our start. Okay. So we want to reset at 0 up until t of the rate. Now I need to use something other than t in here. So 50 e to the 0.3. Doesn't matter. I'll use u. You could use x, v, a, b, whatever you want. I'll use u. Okay. So this is right. We're going to reset accumulating at 0 at this rate up until t, but we need that initial amount to be, so here, what's the initial amount of bacteria in this function right now? 0. So at this reset, we're going to get 0 bacteria, but we need it to be 250. So what can we do? Just add 250. So it's going to reset at 0, and that just the integral part will give 0, but then we'll account for that 250 that we're actually starting with. Does it make sense? Okay, so then before we find the population at 10 days, can you find the closed form version of b of t? Closed form version of b of t. Meaning just a formula now. We just want a formula that has the exact same output as this open form. That means we need to find what? Antiderivative. So what function, this is a little bit harder, what function has this as its antiderivative? So we're going to have a 50, roll on to the 50 here. So we got e to the something. What kind of function gives us a derivative or rate of change of e to the something? E to the something. So you can just start with an initial guess of 0 e to the 0.3u. Take the derivative of that. So do some side work. So go over here. Say, okay, what's the derivative of my guess here? My guess is e to the 0.3u. It's going to be, what, 0.3 e to the 0.3u. Is that the rate function that we started with? No. So how do we adjust our initial guess to make it right? Yeah. Yeah, so when we take the derivative, what's going to happen? We're going to multiply by 0.3, but we don't want that to be there when we're done. So we're going to include a 1 over 0.3. Now when we take the derivative of that, the 0.3 times the 1 over 0.3 will be 1, and we'll just have the e to the 0.3u. Did you see what happened?
Yeah.
We're going to practice more of those, okay? We're going to practice some more. But the key is, take a guess based on the overall structure, and then take the derivative of it and adjust based on what you get when you take the derivative. So we got this extra 0.3 that we don't want, right? So how do we take care of that? Just include a 1 over 0.3. And that's going to be from what to what? 0 to t. We're still doing the function. And then plus 250. So we'll do one more step on this. Let's actually evaluate that. So it's going to be 50 times 0.3 e to the 0.3 t minus 1 over 0.3 e to the 0. And we still have the plus 250. Did you catch it? The total change in accumulation is the final accumulation minus the initial. That is the fundamental theorem of calculus. That the accumulation in open form can be represented in closed form as final minus initial. Please. Yeah.
You got 0.3t up there and then e to 0.
Yeah. 0 times 0.3 is 0, right? Are you saying there should be a 0.3 here?
I'm just asking.
Yeah, what is 0.3 times 0?
0.
Right.
Oh, okay. So we haven't included the 10 yet. Okay.
Yeah, no, I'm still doing the function. Okay, questions? Really important. Are you following everything I'm doing? Could you do it? Did you do it? So what? We got given the rate function. So here's the beauty of this. We've worked all semester for given a rate function. Could we write the accumulation function in closed form? And there it is. There it is in closed form. Not just the integral open form that we need a computer for. Now we can crank out amounts of bacteria by hand. For instance, the bacteria population after 10 days would be B of 10. Which means put 10 there and crank it out. So note something. When you have a limit of integration, this is called a limit of integration, equal to 0, you don't always get 0 when you plug that in. Look at this. This is not 0. So that's a mistake students make, that they see a 0 there. They think, oh, you'll just get 0 when you plug that in. So you just don't have to worry about it. Not true. This is not 0. What is this? E to the 0 is 1. So don't assume that if your reset is at 0, that eventually when you plug 0 in, that thing's just going to be 0 and go away. Here it's not, right? It's e to the 1. So hold on to that. Take it out all the way until you can confirm what that value is. Anybody get it?
Yes.
Tell me.
3,430.92.
So the 31st hasn't fully arrived yet. So really at 10 days, it'll be 3430. Someone else get that? Confirm that? Yes, thank you. Okay. Does the example, super important. I mean, this is using like 80% of what we worked on all semester to do this problem. Good. I'm glad you think so. All right. Let's look at some of these harder antiderivatives. Undoing the chain rule. Recall the chain rule is for finding the derivative of a composite function, one function plugged into another. And what do? So you can do you can do it inside out or outside in. So here I'm writing it outside in, where you have the rate of change derivative of the exterior, keeping that interior function as it is, times rate of change of the interior. Okay? We all know that, right? We all know that, and we're good at that. So what would the antiderivative look like? It looks like that we start with something like that, and we want to recover the original function, g of f of x. So here's the key question. What will you focus on here to recover the accumulation function? You've got basically two things multiplied together. Which one are you going to focus on to recover the accumulation function? Should be obvious. The first or the second? We want to figure out what g of f of x is. What is going to help us do that? The first term in the product or the second? The first, obviously. We're going to focus on that. We're going to find that in order to get that. And then what will our strategy be? How are those different? So how are we going to look at this and try to recover the original function? What will we do to the interior?
Take the antiderivative.
No. Look at it. What will we do to the interior?
Multiply.
No.
You get it. No, no.
What will we do to the interior? The interior is f of x. What is it here? We're not going to do anything. We'll leave it the same. What are we going to do to the exterior? Antiderivative. That's all it is. Right? So as long we just got to identify this part of our given rate function and do the antiderivative of the exterior function. And we got it. Keep the interior as it is. So we're going to write the antiderivative of the exterior function, keeping the interior as it is. And that basically is 90% of the deal. But that, like what we saw in that last example with the bacteria, we had that extra 0.3. We had to deal with that 0.3. So there's might be a little mess that we have to clean up. But that was just the finishing, putting the finishing touch on it. Okay. So our whole approach is going to be to identify this part of the rate function we're given, and then just antiderivative of the exterior function and leave the interior as it is, and we got it. What about this? It's gone. Don't even have to worry about it, right? It's gone. When you do the antiderivative, it's not there anymore. Make sense? Let's practice. Here we go. So again, here's that in review. We're given that thing on the left. We're going to figure out what the g prime f of x part of it is. That's where we're going to focus. We're going to do the antiderivative of the exterior, and we're basically there. So here we go. X cubed, 8 minus x to the 4th, all to the 5th. So think. This is like the result of chain rule. I need to recover the original function g of f of x. So what does it mean? Identifying which part of our given rate function is this. And we need to recover this. So, which part of our rate function is g prime f of x? Is it x cubed, or is it 8 minus x to the 4th to the 5th?
8 minus x to the 4th.
Clearly, here's our composite function. So what is g prime in this case? What's the structure of g prime in the case of this function right here? No, you shouldn't even be looking at this. You should not even be looking at this, right? We're focused on this, and we need to recover the original function. All we need is antiderivative of g. So what is g prime in this function? function? Something to the fifth. G prime. G prime is something to the fifth, so G is going to be to the sixth. So make our first attempt here. What's our attempt going to be? It's going to be, what are we going to do to the inside? Keep it. And what are we going to do to the, add 1. That's basically going from G prime up to the fifth to antiderivative to the sixth. Okay, so now this is a perfectly legitimate first attempt. Okay, and so remember that, what does it mean if you have no limits here? No, it means every possible accumulation function, every possible antiderivative. So that we know we're going to have, so we think of this as like a to x, okay? So we're going to have minus f of a, which is a constant. We just call that plus c, okay? So we're going to have the first part, that's our actually x minus capital F of a, but that will just always be a constant if we're just generically saying every single antiderivative. Okay, so our attempt is going to include this minus f of a, which we'll call plus c. Remember, because it's the difference. Okay, so then what do we do? How can we check it? How can we check our attempt? Take the derivative of this. Ready? Quick. Derivative is 6 times to the fifth. Are we done? Times negative 4x cubed. Derivative of plus c. 0. So now let's simplify this. What did we just get? We got negative 24 x to the cubed, 8 minus x to the fourth to the fifth. Is it the same as what we started with? Right? So we took an antiderivative, then we checked it by taking the derivative. It should be the rate function we started with. Is it the same? What's different about it? The negative 24. So now we want a second attempt. So this is our first attempt. Attempt number 1. So now we just need attempt number 2. Well, how are we going to adjust this so that when we take the derivative, that negative 24 won't be there? 1 over 6? 1 over? No, we want negative 24 to go away. We're getting an extra factor of negative 24. 1 over negative 24. We need that to go away when we take the derivative. Second attempt. Now, so we're hoping now if we took the derivative of that, we'd get exactly that rate function that we started with. Okay, so it'd be negative 1 over 24. So here's the check. Check is over here. Check is negative 1 over 24 times 6, 8 minus x to the fourth to the fifth times negative 4x cubed. And then 6 times negative 4, negative 24 times this is 1. So we're left with 8 minus x to the fourth to the fifth times x cubed. Exactly what we started with. So we got it. All antiderivatives of this rate function. All antiderivatives. Right? Because at different resets, so this plus c, at different resets, we're going to have different values of minus f of a, basic, or f of c, little c. That's what that plus c is. The different resets will mean a different minus starting value of accumulation.
Really quick.
And we just represent that by plus C. Yeah. Yeah. Questions on that? Okay, another example. E to the 7x over e to the 7x plus 9. Okay, so this is harder because, actually I should have get rid of everything first. So the reason this one's a little trickier is because you look at this, well, it's a fraction, not a product, right? So we're expecting, if it's going to be one of these undoing the chain rule, if we're undoing the chain rule, we're expecting a product, but we got a fraction, so we got to start by turning it into a product. Okay, so how can we write this as a product? As e to the 7x times what? E to the 7x plus 9 to the negative 1. Now it's a product. Which of our two factors is g prime f of x? That's our total focus, right? We're going to focus on g prime f of x. First term, first factor, or second factor? Second factor, right? Second factor looks like g prime f of x. So what do we need to do? We need to do the antiderivative of what function? Antiderivative of? No. Something to the negative 1, right? The f of x, the interior, just comes along for the ride. We don't do anything to it. We're focused on the exterior function and getting the antiderivative, which is to the negative 1. What function has a rate of change of to the negative 1? Doesn't work, right? It just drops off. So who knows their mastery rules really well? What function has a rate of change of to the negative 1, or 1 over?
Oh, ln.
Natural log. So our first attempt will be?
1 over ln.
Not 1 over.
No, ln of
Natural log of
7.
e to the, leave the inside the same. Did you catch it? That's our first attempt. Check it. Derivative is 1 over e to the 7x plus 9 times the rate of change to the inside. E to the 7x times 7. Is it the same as our original function? It's close. How do we need to change our first attempt? 1/7, right? We need that 7 not to be there. So if this original accumulation function had a 1/7, it would eradicate that. But then we need all possible antiderivatives, right? All possible antiderivatives. Did you catch it? Okay, so to get ready, so we need to practice this stuff. There's going to be homework, like I said, over the weekend. But that's all studying for the exam. That's all studying for the final, which is Tuesday night, 7 p.m., PSF 166. I'll write it down. Here we go. Tuesday, 7 p.m., PSF 166. I will have a study session on Monday. We'll have a study session Monday. I'll send all the info.
Awesome.
I'll be coming to that session.
Is there a reservation? No.
Hi, Professor.
Hi, what happened?
I really don't want to tell you.
But you really couldn't come.
I really couldn't
You
come
weren't taking
because
advantage of the situation.
I was embarrassed.
No, that's fine. That's fine.
Sorry.
Okay, that's okay.
And I'll see you around sometime.
Yeah. Oh, you're leaving?
Yeah.
When'd you leave?
Tomorrow, Friday afternoon.
Okay, have a safe
tomorrow's
trip.
Friday. I'm in
Yeah,
final
so
low sleep mode.
just hit me up when you get back.
Okay, yeah,
Yeah.
I'll do that.
Cool. Have a good trip.
Okay, so I have a study session for another class
Yeah.
on Monday morning
Okay.
at 9:30 to 11:30.
Yeah. I usually do like middle of the day, like 10 to 2-ish or something like that.
Okay.
Yeah. So that'll work. So who's next?
I'm here for something.
When will the test scores be